project called Fusion Fire. It's a DataFusion database thing that we've built inside of Pydantic for Logfire. I've been in open source for a while, and I've done before I was here, I did data engineering type work, and I've been doing Pydantic stuff, which has been a lot of Rust, a lot of Python libraries for 2 years, and I've been working with DataFusion specifically for about a year. So the outline of the talk today is going to be first going over what Logfire is. That's our commercial observability product. Why we use DataFusion, like try and justify that a little bit, and then I'm going to jump into how we actually use DataFusion. So just a quick point of clarification. It's a little bit confusing what Pydantic and what Logfire is. Pydantic is a very popular open source project that's used in Python for data validation. It's also the name of our company. We're a VC-funded company that's building Logfire, which is a commercial observability product that's not open source. You have to pay to use it. Well, there's a free tier, but you don't get the source code. And then DataFusion is our internal, database thing, or Fusion Fire is our internal database thing built on top of DataFusion. So that's like the terminology that I'm going to be jumping around. So what is Logfire? It's an observability product. We're trying a couple new things. We're trying to make it both so you can use it for analytics, and that's a lot of where DataFusion comes in. We're trying to make it so you can use SQL to access your data. So we're not inventing a new query language. If you want to write a regex, it's super easy. We integrate with LLM, so you can just ask it what you want to write, and everything knows how to write PostgreSQL. So quick demo of what Logfire actually looks like. Let me get new. Can I move this over to this screen? Yeah, okay. Let's go. So I made a quick project. Yeah, I'm moving over now. Did that? No. Oh God. Okay, well, I might just skip the demo in the interest of time, but window. All right, try again. Okay, this is what Logfire looks like when you open it up. And if I can get this other window over here somewhere. What is it? Okay, I am losing my mind with these screens. I'm just going to start sending some data. I just want you to see what it looks like live. Some data start to come in. Yeah, okay. So I just have a little Python script running that's sending data, and the point is this is just a small script, but it's distributed tracing, so you get nesting of stuff, and it's live, so you get data in pretty much real time. This is some Python script sending data, so you'll see it says Python. It'll give you the line number that this was logged from and all that kind of stuff. But really what I want to talk to you today about is actual DataFusion. So let's close this thing. Back to presentation. The point is here, we had some requirements for this product. In particular, I'm not facing that way. We wanted about a second of ingest latency, and I think that's relevant because we're not a real-time product. We're not meant to monitor instruments and take real-time actions or anything like that. We're meant so that if your app's crashing, it's not going to take 10 minutes for your data to get there, but it is pretty fast but not instant. We really want users to be able to write SQL. In particular, we want them to use a reasonable SQL dialect that they could be familiar with, that LLMs know about, that sort of thing. We wanted to support both analytical and transactional type workloads. So there's things where my app is crashing right now. Where is the error coming from? As well as how many users have signed up each day over the last month, or what endpoints are being hit the most? What is my latency on each endpoint? That sort of stuff. And obviously we need low storage costs and just low operating costs, because it's a business where margins are relatively important. So where DataFusion comes in is we have, it's really confusing here with the screen that way. We're OpenTelemetry. So you send us OpenTelemetry data. We take that data, we do some basic auth and stuff, like figure out who's sending it, are you paying us? Do you have enough quota, whatnot? We do some batching and queuing to, not write out a bunch of small files. And ultimately we dump the data into Parquet files, and then we query it with DataFusion. So that last part is where DataFusion really comes in. I'm going to start talking about the batching queuing part, because I think it's just an interesting engineering part. And I think if you look at a lot of these systems, you hear a lot about, how the data is queried and whatnot, and not so much about how the data is ingested. And that ends up being a really important part of the system, especially for us, because we can't drop data. If you're down and then your observability tool is down or is losing your data, that's really bad. So this is kind of what it looks like. We have a client SDK that sends us data. Then we have, the API that does the auth and stuff. And ultimately we write that to a queue. And that queue for now is just a Postgres table, which has turned out to be a really, really great thing in the short term, at least, because it took us like 2 days to write this thing up. And it's been super reliable and has scaled way beyond what, like, this was like, oh, we're going to write this for our, MVP type thing. And then it's been just chugging along. And it turns out we're using like 1% of the Postgres instance we allocated. It's like less than 1 CPU to do all the data, because everything's just like in cache and it flows through pretty quick. But the table is essentially just a spatial batching key, a temporal batching key, and the data. And what we do with that is we say within a second time window, we try and grab data from the same spatial batching key, but we always get the latest temporal window. So if we have one organization sending us a ton of data and another one sending us small amounts of data, we may prioritize the larger one within a second, but over a period of more than a second, we're fair in ingesting data. And that lets us get really good batching while still guaranteeing like a 1 second time window. And it's not, the way we get data out when we pull it out is basically just say, like, yeah, what I said, just do an order by the temporal bucket, always get the latest one. And then within that, order by the spatial bucket, set a limit on that and pull it out. There's some for update skip log stuff in there and limits, but that's the basic idea of it. And then, yeah, on the polling side, we just have some Rust processes running, a bunch of workers in a loop, and just comes and checks for stuff in the queue. And as long as you have more capacity pulling off of it, then, it's not backing up, you're good, and everything's pretty much real time. This is long term. We're probably not going to stick with this. It's scaled way beyond where we thought it was going to. But in the future, we're going to have a similar system, just distributed with SQLite. So instead of having one central Postgres instance, you have, as many as you need. You shard per tenant, send data from each tenant into, one or, a limited number of these things, do the batching there, and then flush it to the query part, the part that's running DataFusion. So that's the next part I'm going to talk about, which is our like metadata store and the DataFusion, the query part. In particular, I'm going to focus on like the metadata store and the indexing and stuff we do, so that data can be accessed quickly, so that queries run in pretty much real time. So fundamentally, our system is right, like a client sends a query, like in this case, select count from records. Where is exception being like a Boolean column representing errors in your application. And then we use DataFusion to parse all that. We use DataFusion to ask our metadata store, which is a Postgres database, what files should I be scanning? And what we do there is so DataFusion, when you ask it to query a Parquet file, it looks at the Parquet statistics and metadata in that file to try and filter out what record batches and what pages and what smaller pieces of the Parquet file need to be read. And we've taken that data and put it in Postgres. So now we don't need to go and download that data from object storage to decide if we should read the file or not. We transform that query into a Postgres query, send it over to Postgres. And Postgres turns out really, really good at running, basic queries, because these end up being really basic queries. They're just like, this column is larger than this number, this column is less than this number. This column is, true, or stuff like that is not null. And so it's a relatively small table, because even if you have a 100 megabyte Parquet file, you probably only have, I don't know, a couple row groups in there. So that ends up being 20, 30, 100 floating point numbers and some strings. So, I think we have like, I don't know, I forgot how many terabytes of data we have now in cloud storage. Our Postgres table is like 100 megs. So the whole thing is like in cache, and these queries are super fast. So within like 5 milliseconds, we can determine exactly which row groups we need to read. And then we get that back into DataFusion. DataFusion goes and reads the data from object storage. We have like some caching layers and whatnot, but essentially hit object storage for the exact pieces of data that you need. DataFusion runs a query and returns the results back to the client. So this is kind of what our metadata store looks like. We essentially have, there's a couple more tables. There's like a tables table that has the list of all the virtual tables that we have. But this is like what the stats table looks like. So you have like essentially like a table ID, a file ID, some row groups, and then the statistics. Like in this case, I'm only showing start timestamp, but for multiple columns, we'll have statistics. This is what's called like a zone map when you have just like the min and max. So it's like the min and max for each row group, for each column, for each row group. And so in this case, the query ends up just turning into, hey, find, if you're filtering on start timestamp, you're going to do something like find, 11, like the 15th of December, I guess this is hours, right? So it's like, or minutes, seconds. So you might say like, hey, anything within that happened on December 15th, I want, but not December 16th. And so that gets filtered out, and ultimately we return file IDs and row groups, and then DataFusion can look that stuff up in object storage. What's really interesting is DataFusion actually does a lot of this work for us, because you can imagine like transforming a user's query into a query on a different table structure is kind of complicated. But DataFusion already does that for Parquet. So we're able to repurpose that stuff to ask DataFusion, hey, here's the query, extract the filters, and then transform those filters into a SQL that I can run on, this certain structure of table that I showed with like min maxes and whatnot. So that process looks something like this. Like if the top was the user's query, the bottom will be the rewritten query. And the point is like you take something like start timestamp larger than now, blah, blah, blah. DataFusion is going to evaluate, like the now and that kind of stuff, and transform it into like the minimum timestamp on that row group has to be larger than this thing. For something like service name, it'll be the minimum value in that row group has to be larger than demo, and the maximum value has to be less than or equal to demo, i.e. like the value demo exists in that row group. And if the service name minimum was like Z and the service name maximum started with Z, then definitely demo is not in that data. So you're not going to get that file ID and row group back. And then because it's observability and it's semi-structured data, there's some stuff called attributes that I'm going to come back to because it's a bit more complicated to deal with. I go back. Yeah, so this is essentially what the data we get looks like, and I call it semi-structured because back in the day when you had like just plain text logs going somewhere, that's very much unstructured data. There might be some structure to the plain text, but it's variable. You have to like parse it, all that kind of stuff. What we get has some structure. So like every single trace or span or log has like a timestamp, some message. There's some other metadata like exceptions, but then there's also essentially unstructured data. And I say essentially because it's arbitrary, it's different for each row. There are some conventions like http.statuscode is what OpenTelemetry calls a semantic attribute. So it has some defined meaning, it has a defined name. Like it's expected that every system sending data is going to send the HTTP status code under this attribute as an integer. And there's things for URLs, Kubernetes pod IP, like all kinds of semantic stuff. But there's also like, I'm just throwing in my own data, right? So like every single user, every single system can put on every single log just different data. In this case, it's like a user ID. It could be like a data frame. It could be, kind of really whatever. And yeah, so these are some examples of like the semantic conventions. Like HTTP status code is one of them. This is some other HTTP ones. Server address, server port. The point is like OpenTelemetry tells you like, hey, if you see this, it's supposed to be a string. Here's the meaning. Here's some examples, that sort of stuff. And this was a major problem to deal with in terms of query performance because one option is you take this stuff and you store it as JSON and like a string column, but then you have no way to index into that. And if someone asks you for something, your only option is to like download all the data, parse all the JSON for every row, go through every row and try and find it. We actually wrote like a custom JSON parser in Rust that is like, I think like 5 times faster than Sturdy or some multiple of Sturdy, which is really cool, but it's still really not good enough because it turns out that even if you made your JSON parser faster, you still are downloading gigs of data, and that's not fast. So what we do with these is we split this up. We say for, the structured part goes into like their own column. So like we have a, timestamp column, a message column. Then we store the original like semi-structured data that we get. So that if you want to do like select star or like download it, it's all there, and it's JSON, and you can download and work with it in pandas or whatever, polars, and it's easy to work with. But then we take the semi-structured stuff and we do what we call like popping it. So we'll take like HTTP status code and put it into a column specifically for HTTP status code. It's like a private-ish column. We think of it as like indexing that attribute. But now we can pre-parse this into an int column. So now it's very efficient to query this column. And the other nice property about that is what's left over, which it turns out is like less than 1% of the data, can go into a unstructured column that's also private, which we can make we don't currently store it as UTF-8, but we plan on making this like a binary format. So not only is it now a lot less data, like less than 1% of the data, it's faster to parse. And this stuff we can properly index, like in our Postgres secondary index. So what happens then when a user writes a query, and this is like Postgres JSON B syntax, which we ported over to DataFusion. They'll be able to select where something where like the HTTP status code is 200, and we'll do a rewrite where we transform that into like, hey, this special column we created is equal to 200. DataFusion even does some more rewrites to say, hey, this column, I know this column's an integer, so I can even drop the cast. So now it's like you're directly accessing that column raw as quick as you can get for an integer. And what happens when someone queries something like username, which was one of the things that was not structured, is we rewrite that to hit this remaining data column that's a binary format that's a lot better compressed, much faster to parse. And we do some rewrites to say, okay, you're trying to get you're doing text access to that. So we have like specialized JSON parsing function that says, hey, I'm going to try and get this as text from that column. Another problem we had with indexing is these things called trace IDs. So essentially, for every in distributed tracing, every log line or every span has its own ID, but they're all grouped in some way. Like this, this was a request that went through these 5 different microservices. There's an ID for that request. It's somewhat arbitrary how you group your traces, but these IDs essentially end up spanning somewhere between I don't know, 5 rows and like 1,000 rows on average. And they're 128 bit numbers, so it's like a UID. It's pretty large. It's somewhat hard to represent and really hard to index, it turns out, because zone maps don't work. They're random numbers. So if you have like 2 of them in a row group, you might have like AAA and ZZZ. So you can't really sort them. You can't do much with them. I wish they were like ULIDs or like temporally sortable, but they're not, and we can't change that. So zone maps don't really work. Turns out Bloom filters aren't even really great either, because you have a lot of distinct values. And even if they worked well, you'd still have to go and download the Bloom filter data for each Parquet file. If you have 1,000 Parquet files, now you're downloading 1,000 different Bloom filters, running through those, and then deciding that I only need to read like a very small subset of one Parquet file. So that's pretty inefficient. So what we ended up doing with these is we put them in our Postgres table. But we didn't just chuck them in there. We store them as a small integer, as a 4-byte integer, and we do that by hashing them and then truncating the result such that we can take this 128 bit thing and compress it into 4 bytes. And then we put it in an array, and now we can query it with as an array in Postgres and as an array overlap. So if a user sends us a query that says we're a trace ID in some string UID, we take that string UID, we put it through the same process to transform it into just a small integer, and then we query that out of Postgres. And there's some details about like using a gist index and using the int array module, which essentially like we have a lossy index. And the point of all of this is that lossiness is okay because everything is going to be rechecked in the end, and false positives are okay, false negatives are not. So we like these queries have a false positive rate, but the point is there might be like 1,000 different Parquet files to start with. Doing this query on in Postgres on this index is going to reduce it down to like 2. Those 2 are going to be downloaded, and DataFusion is going to then run through them and say like actually only one row group has the data you wanted, the other ones are false positive. But we've gone from a query that would have taken 10 minutes, an hour to run because you have to download 100 of these Parquet files and run through all the data, to now it's something that takes like really some of these take like less than 100 milliseconds because it's all it's doing is going to object storage and getting a small bit of data, and that's like 50 milliseconds plus like the Postgres query is like 5 milliseconds. So it's ends up being really, really low latency to get single rows out of Parquet.
Sorry.
Yeah.
Approximately how many trace IDs do you have in that? Like you have an array?
Yeah. These arrays are on average like 100, 200 items each. So it's however many trace IDs are in a row group. So some of them end up being like 1, some of them end up being hundreds, and that really depends on how people are using the product. So that's part of the problem. It's like there was no like, oh, each row group has one trace ID. Like if you try and like sort them or group them somehow in row groups, you end up with like some huge ones, some small ones, some mixed ones. So it's yeah, it's hard to index that sort of thing. So another technique that we've used is what we're kind of calling row group clustering. So traditionally in storing Parquet files in object storage, there's like hive partitioning, which is saying like I take all the files for a specific day and I put those together in one folder, and then the other files for a different day are split out separately. And then within Parquet files, you have row groups, and a very traditional technique is to sort your row groups so that things roughly end up clustered. And there's fancier ways to do this. Like for Delta Lake users, there's like Z order, and now they have they call it liquid clustering. It's just ways to like map dimensions so that the data you want ends up closer together. But we found that for some things in particular, like I want to get rid of this thing. This is like trying to do something in a mirror. I just want to show you the column names. So in particular for like metric names, this was one that was complicated because the cardinality is like in the hundreds. So we found that if you partition into files, you end up with a lot of small files. And like we get an export from our users that's like, okay, here's like 1,000 rows for 100 different metrics, and it'll be like CPU, it'll be like CPU usage for each core in each one of their services or something like that. So then we were taking that and splitting it up into a lot of small files. And that was not good because it meant more rows being written into metadata store. It meant smaller Parquet files with more overhead. And then the other end of that was like, okay, you put it all in one file and then you sort your row groups by that. But the problem we found with that is if you have like some metrics send a lot of data, some metrics send little data. So then you end up with like one metric with a lot of data, one row for your metric with a little data, a lot of rows for some other metric in a single row group. They're sorted, but if you have very little data for a metric, that's going to end up in a big row group with some other stuff. And the unfortunate part about that is then this thing that's smaller and has less data, which you think should be fast to query, is just as slow as the big thing because you have to download an entire row group. It's somewhere in that row group, but you have to download a lot of data to end up with very little data. So what we ended up doing is we sort our entire files, by some columns like say service name and CPU or metric name in this case. But then we cut off the row groups on some columns that we cluster by, such that we know that in each row group there can only be one combination of service name and metric name. And then there's other columns within that. And that lets us be able to very quickly look up like CPU usage for this service. Because most of the queries on metrics are going to be like plotting a dashboard or something like that. So you might want to find, all the metrics for your service, or really more, it's usually like, I want to find all of the CPU usages and plot those and, categorize it by service. And the really nice property about this is that the whole file is still sorted. The whole file is still sorted by those columns. So we can pass that off to like DataFusion and say, hey, this file, all this data is sorted, and that allows some other optimizations and stuff. And we can also sort, by further time columns. So we can like sort by timestamp within those metrics. So that lets us keep using a lot of the optimizations, but we just happen to cut off each row group per clustering column, so that then we have those statistics in our metadata store. And so looking up, CPU usage for the service API, again, becomes like you hit Postgres, that's 5 milliseconds. Then you go and you get the data, exactly the data you need from object storage. So, 50 milliseconds or so, plus whatever time needed for aggregations and stuff like that. So we've done a lot of work to make our system faster through indexing. And I think that is DataFusion is very fast in terms of it does vectorized stuff wherever possible. It's written in Rust, it's very performant. But if you just throw it at a bunch of Parquet files in S3, and you tell it, hey, list out these files, the latency of listing those files, the amount of data you're downloading to, get small data, to filter client side and get small data back, ends up being a lot. So we've had really good luck with that, but there's still a lot of problems that we have for tomorrow. In particular, like one of them is we support dashboards in our product. So it's like, yeah, plot CPU usage over time is a simple one, but a lot of them involve like relatively complex aggregations. And we found that even if you have a lot of that data cache and memory on SSDs, whatever, still you have to get that data and do all those calculations. And every time someone refreshes the page, you got to do that again. So we want to develop some sort of like cached aggregates. Timescale is a feature called continuous aggregates that's similar. Essentially, like you define a query, and then you as data comes in, you compute that and you save it somewhere. And then maybe you populate that cache thing every few minutes or something, such that when someone loads a query and says, I want this complex aggregation for the last month, you don't have to go and recalculate it for the last month. You may recalculate it for the last like 5 minutes or something, because the data for 3 weeks ago is not changing. But currently we recalculate every time. We also want better caching strategies. So I'm excited for Xiangping's talk today, because yeah, we currently like we cache stuff, but we cache at like the entire file level, and we cache the Parquet, and we found that like, yeah, even if you have the thing in memory, just like decoding the Parquet and filtering it to only then decide that, oh, I only need 5 rows from it, is really expensive. So we want to do something like what you're going to be talking about, I don't know, maybe storing it in Arrow and filtering it, doing the filtering on the cache. Then we're also working on tweaking pruning predicates that DataFusion generates. Like our Postgres index, like I said, it's like a small table. I think it's like a couple hundred megs or something right now. And so actually we end up sequential scanning it for the most part. Like we say like, hey, these are the rows that correspond to the table that's being queried, but then sequential scan within those, and up to a couple, 1,000 or 100,000 rows is actually fine. But we know that that's not going to scale infinitely. So we're working on tweaking how the predicates get generated, so that we can have indexes on the statistics themselves in Postgres. So now if you want files with a start timestamp larger than something, we can filter down to just the files in that time range, and then scan the rest of those statistic rows. And those are kind of the DataFusion things. Then there's like other parts that are just interesting of building a query engine system, and like one of them is like noisy neighbors. Like it's a hard one. It's like, okay, so you set up DataFusion, right? And now it's like you have it running, and you get one query, you get another query, everything seems fine until someone sends you a really heavy query, and then someone sends you a light query, and now that light query is all of a sudden timing out because the other query is going to time out anyways, and so everything's now timing out and no queries are running because one person sent a bad or like a heavy query. And it's really hard to know ahead of time what queries are heavy, what queries are not, and so that's it. When you have like an observability product, that really sucks, because someone's going to be like, hey, my thing's not loading. It's like, oh, some other random person sent a query and that's why your thing isn't loading. That's just like not an acceptable user experience. So and these are problems that are not, I think kind of like some of the indexing problems have like a solution. Like, you add a Bloom filter, you store your metadata somewhere lower latency, things like that. these ones are just like problems that, from what I've seen from other systems, you just engineer it and engineer it and engineer it until it's not that big of a problem anymore, but still exists. And so these are the things we're going to have to solve going forward to be able to offer, you know, good user experience in querying. And that's it. That's my talk.
On the storing of stuff, where you
Yeah.
were, you kind of pulled things out. Great idea in terms of doing. Did you experiment around with any of the container types in Arrow and DataFusion, maps and things like that, and storing against that versus?
Yeah. So you mean like the JSON stuff, like storing as a map?
Yeah.
Yeah. So like if you store it as a map, I think you might get like faster lookups on like the top level keys. We can't store it as like map union stuff all the way down because it's infinitely recursive in theory. So you can't express infinite recursion in Arrow data types. And the performance is just not great if you start doing that. Like I said, like and the other problem with that is like for users querying your data, like it's a much better experience if you just get some JSON text back. Because although as like inefficient or whatever as that is, like you can see it and understand what it is. There's everything can parse and work with JSON. You know, like even data frames have specialized functions. Databases have specialized functions. So if you're pulling the data and doing something else with it, it's really nice that it's in JSON and not like map, list, whatever. But part of the point of what we did of like splitting out the semantic stuff and having like the remaining stuff is that remainder is now like our private thing. So like I said, we're going to do some sort of binary format for it. We haven't decided yet if it's going to be like, oh, we use an Arrow map at the top level, and then the values are further recursive, but they're, you know, just JSON or some other binary thing, or if it's going to be all like a binary column with a specialized format. But yeah, that's basically where we might end up using that stuff, but not at the top level. Yeah.
Like you have like the kind of like open telemetry spec is kind of like, you know, it kind of like drives your schema, you know,
Yep.
a lot. So like, have you had to deal with a lot of like, you know, as the schema changes, or if you need like add columns or whatever, like how do you like manage it across, like, you know, you have it represented in the metadata store, the existing Parquet files, new Parquet files, kind of how do you guys approach like evolving the schema over time?
Yeah, so essentially we have like you can't edit the old data. That's like, because if you ever tried to like, I don't know, like add a column to a Postgres database with some huge table, and like you said the default value and do update table, now it's going to run for like hours because it has to rewrite your entire table. So that's like really not an option, especially when you have like terabytes and terabytes of data stored in Parquet. So what we do when we add a column is we do schema adaptation. So when we read it back, you need to essentially accept that if you add a new column, old data is going to have nulls. Or we've gone kind of a step further and taken like DataFusion's like schema adapters and said, for example, like with the HTTP status code thing, right? Where we said, okay, we added this we broke out this new column, we like indexed it, but we want all queries to be able to refer to that column. We have schema adapters that generate columns. So like it'll on the fly, it says, oh, this old file doesn't have HTTP status code as its own column. I'm going to do the slow thing and parse the JSON and like grab it out. And the point of that is that queries will all still run, and most of the system can like, you know, assume that that column exists. And it's just like at the very boundary where you're reading the file that you like generate that column on the fly, so that, you know, you don't get errors or anything like that, and you don't get nulls and whatnot. Yeah.
I like this clever idea of putting your loss in this. It's probably not too difficult to figure out like how you're going to scale that, because like the worst thing that can happen is your company becomes extremely popular. Now.
It's not the worst thing that can happen, but yeah.
Well, it is. It depends. If you have stock options, it's a great thing.
Yeah.
Just an engineer, it's a bad
Yeah. I get you.
It keeps you employed.
Yeah.
But
Several engineers
the
dream a nightmare.
question is like, have you considered much about scalability? Right?
Yep.
Because like at some point you have so many things going in that now you just reproduce the original problem, and like my queries are taking forever because I have so many things are colliding.
Yep.
It's like the equivalent to a hash map. Like I got so many returns, so many false positives that it's potentially the type of thing where you just like increase the size of that index just a little bit, and boom, problem goes away.
Yep.
But have you figured out like what your tipping point is at which you would?
Yeah. I mean, it's a great question. I think like there isn't one answer to that in general, in the sense that like, yeah, okay, we have a Postgres table that's like 100 megs, but if we like 1,000x our volume, now that's too big of a table or something. And that's why we're like trying to like rework trying to get ahead of this problem by saying like, okay, at some point we're going to need indexes on the index. And so we need to rework how the predicates that get generated work so that we can use indexes more effectively in our metadata store. I mean, part of it is just trying to design it. So like I said, we have like terabytes and terabytes of actual data, but only like a couple hundred megs in our metadata store. So that's 100 megs is nothing for a Postgres table. So the idea is that, like we'll be able to scale that quite a bit. And when we hit the limit on that, there's a pretty easy solution, which is, hey, we have distinct actual tables, and, we can shard by table. So DataFusion does the work of like parsing. If you have a join, DataFusion already does the work of parsing that and saying like, okay, I'm going to scan these 4 tables and then I'm going to join them or whatever. So from our point of view, as we implement what's called like a table provider in DataFusion. So in theory, we can have each table provider hit a different Postgres database. Typical like charting stuff. You take like the tenant ID or something, say, oh, this tenant ID maps to this Postgres database or something. And ultimately, if we have a client that's like so big that they're taking over an entire Postgres instance, then like that's a good problem to have. And you ask them to, you create a enterprise plan and charge them for their own Postgres database. So that's kind of how we view the scaling. It's like, try and design it so that like we have headroom, try and get ahead of the problems. And at some point we've tried to make it in a way where we can scale with tradition. We want to have traditional problems, right? Like we want to get to the point where the problem is we need to chart our Postgres database, because that's a solved problem, right? We don't want to get to the point where we created our specialized, index thing, and now we need to scale that. And how do you do that? It's not designed to be scaled. We want to have the problem where like we have a Postgres table that's not used analytically, it's used transactionally. Like every time a new file gets written, a new row gets written in. There's a column that you can shard by. You can tune out a vacuum, like those. We've already had to do some of that. Like we had in this table, although it's pretty small, there was like a lot of reads and writes going, and we had a point where like auto vacuum started to not keep up, so there was like more and more dead tuples, and we had to like tune out a vacuum. But that was like you look at it, you tweak some numbers, you read a blog post, and it's kind of you solve the problem.
Thankfully, someone asked a second question. So the problem of balancing file size, number of files.
Yep.
Like I think that's certainly one of the weak things. It sounds like a great thing to build like observability.
Like the size of row groups and stuff.
Well, so like when you're deciding how to break your data, whether it's in separate files with certain types of row groups, or bigger files or smaller files, like and coming to the right balance where you're querying just the right amount of data, not too much, but you're also not spending all your time with
overhead and exactly.
Oh, I need to get 10,000 20 megabyte files.
Yep.
Garbage, right? So it seems to me like that is a perfect opportunity, maybe not for what you're doing here, but something that really could benefit from building an observability solution around, or maybe not what you're doing, but larger data.
Yeah. I mean, well, one of the really interesting things about building an observability platform they found out is how do you observe your observability platform?
Yeah.
It turns out that's actually a relatively hard problem because you can't use any other observability tool. Like at first we were like, oh, we'll just go and we'll use like Datadog for our observability, so that if like, obviously we're going to use ourselves in dog food, but it's also like, if you go down, then what do you use? Turns out you can't use anyone else because they all have terms of service that says you can't build a competing product, except like maybe the cloud providers. So we actually like use ourselves to observe ourselves. And that was really, really difficult at first because, when you first start the product, you're like falling over all the time. And it was like, oh, we're down. And so we can't know why we're down. But now it's a lot more stable and it works pretty well. So like with like the row group size and stuff, we have like a ton of metrics. Metrics are, for those not familiar with observability, are like, it's like a reduced view of your system. So if you have latency, you're gonna export like a histogram of latency instead of like every time I get a request, I say this is how long it took. You like accumulate that and like pre-aggregate it essentially and export that. So we have like metrics on like, row group sizes and file sizes and time spent writing and time spent reading and how many files are being run for each query, and like we actually even wired up DataFusion so that every query that's run exports like the equivalent of explain analyze, and then we like transform that into like equivalent to like Postgres's explain analyze. So in our own observability, like every query that runs in, I can just click on it. And I would show this to you, but I've struggled enough already with the screen and stuff, so I'm not going to. But like every query that comes into our system, we have this explain analyze, and so you can go and look at like the latency and whatnot, but also go and look at the explain analyze plan and see like how many files were read, how many row groups were pruned by the Bloom filters, how many row groups were pruned by the secondary index and statistics, et cetera, et cetera, et cetera. Any questions?
So you just mentioned the Bloom filters. Are you using the like Parquet
Yep.
built-in ones?
Yep. So I mean, essentially the way to like think about this whole thing is like you just have like layers, and your goal is to like eliminate as much data as you can at each layer, right? So like it's a bit fuzzy what the layers are, but for us primarily it's like query comes in, we go and ask our Postgres metadata store like, hey, which files and row groups do we need to read? And we do our best as best we can to prune there, because again, that's like 5 milliseconds gets rid of like 99.9% of the data. I mean, depending on how selective the query is. Then we go back to DataFusion, and DataFusion actually does the work of saying, okay, you're filtering on this column. I'm gonna go get the Parquet metadata. Does it have a Bloom filter? I'm gonna get the Bloom filter. I'm gonna filter based on the Bloom filter, and then go get the data that I actually need based on that. And then once I have all the data, I'm gonna do more filtering on data and do late materialization, like where it doesn't even like parse the like if you're doing select star, it won't like parse the star part from Parquet until it's filtered on your filter columns and some shenanigans like that. But yeah, the goal is to like take like terabytes and terabytes of Parquet data, filter it down, filter it down, filter it down, filter it down until you say like, okay, this is the data I'm just gonna now grab, and I'm gonna run through it like as fast as I can, being vectorized and being written in Rust and all that kind of stuff.
Is the access into Parquet via like the Parquet access plan stuff that I think was like relatively recently added, so you can like you tell the Parquet scan.
Yep.
These are the row groups.
Exactly. Yeah, we don't do page level stuff. I think that is kind of what Tim is getting at, is like, what is the balance of like file size and row group size and all that kind of stuff. And like at one point we had to decide, do we index pages in our metadata store, or do we index row groups? And we decided to go for row groups because it, just some basic math said that that like is the right coarseness. And also that means that DataFusion can then go to the Parquet file and do further page pruning. So it's like, it's like two levels of pruning. Awesome. Well, thanks everyone.